Good morning to all of my students. Myself, Mr. Dibyendu Mondal, Assistant Professor of Mechanical Engineering Department of Greater Kolkata College of Engineering and Management under JIS Group. In this pandemic situation, I am delivering my lecture through online mode and my video is uploaded in YouTube. Good morning. Today, I am discussing about deflection of cantilevers. Introduction: cantilever is a beam whose one end is fixed and the other end is free. So, deflection of a cantilever when they are subjected to various types of loading. The important methods are double integration method, Macaulay's method, moment area method, and energy method. So deflection of a cantilever, actually deflection of a cantilever with a point load at the free end by double integration method. A cantilever AB of length L fixed a point fixed at point A and free at the point B, carrying a point load at the free end B as shown in figure. AB shows the position of cantilever before any load applied, whereas AB shows the position of the cantilever after loading. So AB total length that is equal to L, one is the X, another one is the L minus X. Consider a distance, consider a section X at a distance X from the fixed end A. The bending moment at the section is given by Mx, that is equal to minus W into L minus X. But bending moment at any section is also given. M is equal to EI d square y by dx square. Equating the two values of bending moment, we get EI d square y by dx square, that is equal to minus W into L minus X. So the minus WL plus WX. So integrating the above equation, EI d square dy by dx, that is equal to minus WLX plus WX square by 2 plus C1. Now, EIY equal to minus WL x square by 2 plus W by 2 x cube by 3 plus C1x plus C2. Where C1 and C2 are constant of integration, their values are obtained from boundary conditions. At x equal to 0 and y equal to 0, x equal to 0 dy dx equal to 0. By substituting x equal to 0, y equal to 0 in the equation, we get 0 equal to 0 plus C2. So that is equal to C2 equal to 0. By substituting x equal to 0, then dy dx equal to 0. This equation we get C1 equal to 0. Substituting the value of C1 in equation, EI dy by dx, that is equal to minus WLX plus WX square by 2. That is equal to minus WLX minus x square by 2. The equation is known as slope equation. We can find the slope at any point on the cantilever by substituting the value of x. The slope and deflection are maximum at the free end. This can be determined by substituting x equal to L in this equation. Substituting the values of C1 and C2 in this equation, EIY equal to minus WL x square by 2 plus WX cube by 6. So that is equal to minus WL x square by 2 minus x cube by 6. This equation is known as deflection equation. theta b slope at the free end b and dy dx at b, that is equal to theta b, and yb, that is the deflection at the free end b. So substituting theta b for dy dx and x equal to L in equation 3, we get ei theta b equal to minus w L dot L square by 2 equal to minus w L square by 2. Therefore, theta b equal to minus w L square by 2 ei. Negative sign shows that tangent at B makes an angle in the anticlockwise direction with AB. So theta B equal to minus WL square by 2 EI. Now substituting YB for Y and X equal to L. So EI YB, that is equal to minus W L dot L square by 2 minus L cube by 6. So that is equal to minus W L cube by 2 minus L cube by 6. So that is equal to minus W L cube by 3. So YB, that is equal to minus W L cube by 3 EI. Downward deflection YB is equal to W L cube by 3 EI. Deflection of a cantilever with a point load at a distance A from the fixed end. A cantilever AB of length L fixed at point A and free at point B and carrying a point load W at a distance A from the fixed end A. So theta C, that is the slope at point C, YC, that is the deflection at point C, and YB, that is the deflection at point B. The portion AC of the cantilever may be taken as similar to cantilever. Theta C is equal to W square by 2 EI. YC is equal to WA cube by 3 EI. So the beam will bend only between A and C, but from C to B it will remain straight since bending moment between C and B is 0. Since the portion CB of the cantilever is straight, therefore slope at C, that is equal to slope at B, theta C equal to theta B, that is equal to W square by 2 AI. So YB is equal to YC plus theta C into L minus A. So WA cube by 3 EI plus WA square by 2 EI into L minus A. Now a cantilever of length 3 meter is carrying a point load of 25 kilonewton at the free end if the moment of inertia of the beam equal to 10 to the power 8 millimeter to the power 4 and the value E equal to 2.1 into 10 to the power 5 Newton per millimeter square. Find the slope of the cantilever at the free end and deflection at the free end. Given length L is equal to 3 is equal to 3000 millimeter, W is equal to point load 25 kilonewton, that is equal to 25,000 Newton. I is equal to 10 to the power 8 millimeter to the power 4 and value of E 2.1 into 10 to the power 5 Newton per millimeter square. Slope at the free end is given by equation theta B WL square by 2 EI. So 25,000 into L square 2 into 2.1 into 10 to the power 5 into 10 to the power 8. So that is equal to 0.005357. Deflection at the free end is given by the equation YB WL cube by 3I. So 25,000 into 3000 cube divided by 3 into 2.1 into 10 to the power 5 into 10 to the power 8. So a cantilever of length L 3 meter is carrying a point load of 50 kilonewton at a distance of 2 meter from the fixed end. I equal to 10 to the power 8 millimeter to the power 4. E equal to 2 into 10 to the power 5 Newton per millimeter square. Find the slope at the free end and deflection at the free end. Length L is equal to 3 meter. So that is equal to 3000 millimeter. Point load W equal to 50 kilonewton. So that is equal to 50,000 Newton. Distance between the load and the fixed end A equal to 2 meter. That is equal to 2000 millimeter. I equal to 10 to the power 8 millimeter to the power 4. Value of E, so that is equal to 2 into 10 to the power 5 Newton per millimeter square. Slope at the free end is given by the equation theta B, that is equal to W square by 2AI. So that is equal to 50,000 into 2000 square divided by 2 into 10 to the power 5 into 10 to the power 8. So that is equal to 0.005 radian. So deflection at the free end is given by the equation YB, that is equal to WA cube by 3EI plus W square by 3EI. So 5000 into 2000 cube divided by 3 into 2 into 10 to the power 5 into 10 to the power 8 plus 50,000 into 2000 square divided by 2 into 2 into 10 to the power 5 into 10 to the power 8. 3000 into 2000. So 6.67 plus 5. So that is equal to 11.67 millimeter. Deflection of a cantilever with uniformly distributed load. A cantilever AB of length L fixed at the point A and free at the point B and carrying a uniformly distributed load of W per unit length over the whole length is shown figure. Consider a section X at a distance X from the fixed end A and the bending moment Mx equal to minus W L minus X L minus X by 2. So bending moment at any section is also given by equation as M equal to EI d square y by dx square. Equating the two values of bending moment, we get EI d square y by dx square equal to minus W by 2 L minus X whole square. So integrating the above equation, we get EI dy by dx, so that is equal to minus W by 2 L minus X whole cube by 3 into minus 1 plus C1. So integrating again, we get EIY, that is equal to W by 6 L minus X whole to the power 4 divided by 4 into minus 1 plus C1x plus C2, where C1 and C2 are constant of integration. Their values are obtained from boundary conditions which are at x equal to 0 and y equal to 0. By substituting x equal to 0, y equal to 0, 0 equal to W by 24 L minus 0 whole to the power 4 plus C1 into 0 plus C2. So WL to the power 4 by 24 plus C2. C2 equal to WL to the power 4 by 24. So by substituting at x equal to 0, dy dx equal to 0 in equation, we get 0 equal to W by 6 L minus 0 whole cube plus C1. So that is equal to WL cube by 6 plus C1. So C1 is equal to minus WL cube by 6. Okay. Now substituting the value of C1 and C2 in equation 1 and 2, we get EI dy by dx that is equal to W by 6 L minus x whole cube minus WL cube by 6. So EIY that is equal to minus W by 24 L minus x whole to the power 4 minus WL cube by 6 plus WL to the power 4 by 24. This equation is known as slope equation. Theta b that is the slope at the free end. Okay, theta b that is the slope at the free end. YB that is the deflection at the free end B. So EI theta b that is equal to W by 6 L minus L cube minus WL cube by 6 minus WL cube by 6. Theta b is equal to minus WL cube by 6 EI. So that is equal to minus WL square by 6 EI. So EIYB that is equal to minus W by 24 L minus L to the power 4 minus WL cube by 6 into L plus WL to the power 4 by 24. So YB that is equal to minus WL to the power 4 by 8EI. So therefore downward deflection at V YB that is equal to WL to the power 4 by 8EI. A cantilever of beam of length 2.5 mm carries a uniformly distributed load of 16.4 kN per meter length over the entire length if the moment of inertia of the beam 7.95 into 10 to the power 7 mm to the power 4. Length L equal to 2.5 mm equal to 2500 mm. W is equal to 16.4 kN per meter. So total load W is equal to W into L. 16.4 into 2.5 41 kilonewton, so 41,000 Newton. The value of I is equal to 7.95 into 10 to the power 7 millimeter whole to the power 4. So value of E that is equal to 2 into 10 to the power 5 Newton per millimeter to millimeter square. Let YB that is the deflection at the free end. Okay. Now a cantilever of length L 3 meter carries the distributed load over an entire length. If the deflection at the free end 40 mm, find the slope at the free end. Given L equal to 3 meter that is equal to 3000 meter, deflection at the free end that is equal to 40 mm. Theta b is equal to slope at the free end. Using the equation YB is equal to WL cube by 8EI. So 40 equal to WL square into L divided by 8EI. So WL square into 3000 divided by 8EI. So that is equal to WL square by EI. 40 into 8 by 3000. Therefore slope at the end of the given equation theta b minus WL square by 6 EI minus WL square by EI into 1 by 6 minus 40 into 8 3000 1 by 6. So WL square by EI that is equal to 4 into 8 40 into 8 into 3000. So the answer will become 0.01777 radian. So that is the slope at the free end, and that is equal to something radian. Okay. WL square by EI, so 40 into 8 divided by 3000. Okay. Okay. Last, if you like my video, you have to subscribe. Okay, thank you.